Well, good evening, everyone, and welcome to Working Rangelands Wednesdays, where we explore topics around rangeland agriculture in California and across the West. This is the sixth and final webinar of our second series, which is all about managing drought in 2022. The first series that we hosted in summer of 2020 also focused on drought management. So if you're interested in checking out those recordings, all of them are available on our Working Rangelands Wednesdays YouTube channel, and we'll drop that link in the chat. My name is Grace Woodmansey, and I'm the Livestock and Natural Resources Advisor in Siskiyou County.
And I'm Dan Macon with the challenging mute button, and I'm the Livestock and Natural Resources Advisor in Placer, Nevada, Sutter, and Yuba counties.
And I'm Leslie Roche, Associate Professor of Cooperative Extension at UC Davis.
So before we get started, we are recording this webinar and it will be posted later on our YouTube channel. And for our live webinar participants, we ask that you use the Q&A feature, which is located at the bottom of your Zoom screen, to type your questions. We'll be monitoring the Q&A, and we'll have time after the presentation for questions. So tonight's discussion is all about drought forecasting and remote sensing. And we have Dr. Leslie Roche here to talk to us and give a presentation on that. And Dr. Roche is the Associate Cooperative Extension Specialist in Rangeland Science and Management in the Department of Plant Sciences at UC Davis. Her research and extension program is at the intersection of agricultural, environmental, and social aspects of ranching and livestock production on California's rangelands and pasture lands. Leslie completed her PhD in ecology at UC Davis and was a USDA NIFA postdoc fellow in the Department of Plant Sciences before joining the faculty in 2015. So with that, I'll turn it over to you, Leslie.
Thanks, Grace. So let's see if I can share my screen here. All right. Are you seeing it? Okay, great. Okay, well, like Grace said, I'm going to talk a little bit about some new work that we've been doing on rangeland remote sensing for climate resilient ranches and rangelands in California. So a little bit of context. First want to acknowledge our very extensive list of partners and collaborators that we have working on this project, particularly the newly minted Dr. Grace Liu, who did a lot of, actually did the majority of the model crunching and all the work that I'm going to show you. So to give a little bit of the context of California rangelands, I'm going to back up a little bit. And rangelands are incredibly biologically diverse, particularly in California. They span a diversity of environments and range types and climates. They cover about 57 million acres, which is a little over half of the land area in California. And about 34 million of that is grazed by livestock. This diversity contributes to a lot of growing season differences. We have annual versus perennial systems. And we've got a range of climate zones from desert to semi-arid to Mediterranean climate. So this diversity supports what we call transhuman ranching, where livestock are moved between pasture-based forage resources in a seasonal cycle. Typically from lowlands in the winter, like the annual grasslands, into higher elevation lands in the summer, such as mountain meadows, as well as other perennial grasslands. And this, of course, creates interdependencies across the state between these different ecosystem types. Now, California's annual rangelands, kind of where I'm zooming in on here, these are winter growing systems. They include both our grasslands, our savannas, and our oak woodlands. They cover about 15 million acres in the state, and they are incredibly biodiverse. They are one of the world's biodiversity hotspots. It's been recorded that we've had over 300 vertebrate, 5,000 invertebrate, and 2,000 plant species alone in these systems. So incredibly diverse. These systems have great social, ecological, and economic value, and so they're often the focus of conservation, restoration, and of course management. They are largely privately owned, and they are the major forage base for the state's livestock herd, supporting about 70% of that forage base. And so they're a key linchpin in California's yearly grazing calendar, and therefore, provide that critical economic foundation. Now, annual rangeland forage production. So California's annual rangeland productivity is extremely variable, in part because of the plant community phenology is dynamically linked to seasonal weather patterns. And this is, one of the key challenges is that the optimum temperature and moisture conditions for plant growth are out of sync with each other in the system. And so this is a bit of a cartoon of annual plant growth rate throughout the entire growing season. And so if all goes well in a typical year, the annual rangeland growing season is initialized by fall rains in kind of the September through December period, which is about where we are now. During the winter months, so December through February, plant growth slows due to low air temperatures and lower solar radiation. And then we start to see a ramp up in the late winter, early spring, on this period here where rapid growth begins as air temperature increases and solar radiation intensifies. And then in mid to late spring, so kind of this period here, after that rapid growth stage, we see plant production kind of the growth rate peaks out, and we get to peak biomass once that root zone moisture is depleted. So the result of all of this is we have extremely high variability in both space and time and forage productivity, due to both that characteristic biophysical and climatic diversity that I mentioned, as well as this dynamically linked phenology of the annual system. And so, what is the result of that? Well, forage production can vary greatly, both between locations in a given year. This is, same year, two different locations, a coastal site and an inland site down the Central Coast. And then they can also, production can also vary, within a single location across years. So these are those two same sites in a wet year versus a dry year. You see, we have tremendous variation here. This variability further is increasing as the climate changes. We're seeing increasingly large year-to-year fluctuations and instability of the forage supply, especially, given a projected warmer and drier climate and increasing trends in weather extremes, such as prolonged drought. Therefore, it's critical to quantify and really understand what are the driving variables of this, spatial and temporal variability in forage production. And so this is what we've been trying to do, really hone in and quantify these factors. And of course, as we all know, drought is the rule rather than the exception in California, and had a shaping force on the landscape for millennia. Climate change and weather extremes, specifically threaten these systems, which are largely rainfall dependent and therefore greatly vulnerable to drought. And the impact of drought on the rangeland economy is likely one of the most devastating climate linked events for the ranching community. And so over the last decade, we've been directly working with ranchers and rangeland managers to better understand drivers of impact, adapt capacity, and vulnerability to drought. And this is some work that we've been doing in rangeland adaptive decision making. A fairly large group of us, including Dan and Grace, my co-host today. And this basically emphasizes how the sustainability of ranching operations depends on their ability to adapt over time to changing social ecological systems in which they're embedded. And so if we zoom in, we're zooming in here into the individual adaptive decision space. We've been specifically examining how individual drought adaptation is enhanced by decision-making factors. And so what we found here, and this is also, again, been work that we've been working on quite a while now, but we found that things like, a big flexible toolbox, the resource toolbox, information sources, and goal setting all positively contribute to drought adaptation and enhance capacity to adapt to drought. So thinking from a cooperative extension perspective, thinking from an applied science perspective, what can we do to help bolster these areas and to help folks increase their capacity to adapt to drought. And so ranchers, rangeland managers, one of the things that's really become apparent is they need spatial information delivered rapidly to both manage risk and mitigate impacts associated with these climate-mediated events, like drought, which is such a prevalent theme in sustainable rangeland management. Sustainable management of forage resources, is a critical goal for producers and a key factor in decision making. And the recent leaps and bounds that have been occurring in satellite-based remote sensing technologies are really providing some big opportunities to put together, cost-effective, near real-time, and potentially forecasting tools to help folks monitor, forage productivity and help bolster that decision-making process. In California specifically, given the high spatial and temporal variability that I talked about a little bit, that is unique to our annual rangelands, there's also need for locally calibrated, trusted decision support tools to help folks, really proactively plan for drought risk. And we've learned a lot about, how following California's historic statewide drought, compared to previous work that we had done before that historic drought, we found that there is an increase in, in interest in proactive drought practice adoption. In fact, a lot of the work that Grace has done and spoke about in this Working Rangelands Wednesday series is, that's based on that. And so we've been thinking about, more, how can we help with more proactive forward planning and create management tools that folks will actually, use, actually need, and actually see value in. And so here we go. We're looking at, okay, so how can we predict forage productivity on California rangelands? And one of the first things we looked into was, questions we looked into is, okay, so what are the main drivers shaping the spatial patterns of forage production in California rangelands? And so, we really looked at how, how climate environmental factors regulate annual grassland forage production spatially across different ecoregions in California. Also, and looking at how does drought versus wet conditions, how do they alter these relationships? This map here just shows you how much productivity has changed over the years from about 2004 to 2017. You just see the immense amount of variability from year to year there, and from region to region. And so what we did is focusing in on the annual grasslands, which are here in green. We split up the area into 4 broad ecoregions. So we have the Northern California Coast Ranges, the Northern California Interior Coast Range, the Sierra Nevada foothills, kind of long strip here, and then the Central Coast Range. And these are divided based on climate and biotic factors. And so we looked at estimating annual forage production over an extended period of time, about 2004 to 2017, using satellite images and some data fusion techniques. And this satellite information was calibrated and validated based on the-ground grazing exposures that were placed in each of these different ecoregions. We had 7 about 60 by 60 meter exposures. And what we found was this satellite-based estimation actually agreed really well with independent field with these independent field measurements. And so looking at, what are the drivers shaping spatial patterns of California rangeland forage production? This is the predicted long-term mean forage production map. You can see the immense amount of variation here. So it's not working. There we go. Okay. So, and in addition to, just predicting the amount of variation here, we also want to look at, so what are the factors that are driving this variability in space? What are the climate and environmental factors? And so we examine the relative contribution of each of these factors as predictors to these spatial patterns forage production, looking at what we call feature importance. So basically, this is just most important in the model for explaining this variability, ordered down to least important. And what we found was that the most influential variables controlling spatial variation were the total amount of precipitation and that monthly distribution of precipitation. How even was that distribution throughout the entire year? Then we drilled down and we looked at this. So that was at the state level. Then we drilled down and looked at this at the ecoregion scale. So dividing those up into the different ecoregions. And we found that for drier regions, generally like the Central Coast Ranges or Sierra Nevada foothills, we found that the spatial variability was influenced by the total amount of precipitation. You can see here, here and here. And then in wetter regions, in contrast, like the Northern California Coast Range and the Northern California Interior Coast Range, they were more strongly impacted by other factors. So you can see kind of the relative importance of the different factors here. I'm gonna have to drop that. They all kind of came, they all kind of became more equal in terms of their importance, as opposed to like in the Sierra Nevada foothills here, you can see precipitation amount is clearly dominant. Whereas in these, we start to see things like energy and temperature become more important, and also precipitation distribution. And so that's just looking at what is the importance. So we know precipitation, total precipitation, and we know distribution of precipitation throughout the year are important, but what is their actual impact on the ground? How do they actually affect forage productivity? And we found that, just zooming in here, we looked at a lot of different variables. I'm just going to zoom in on those top two. So growing season precipitation here, and then precipitation distribution. We found that forage production increased rapidly with increase in growing season precipitation. So not surprising. And we found that areas with more evenly distributed precipitation. So this kind of this lower indicator here. This is more uniform and more even precipitation throughout the year. This is less uniform precipitation throughout the year. We found that these areas with more even distribution had higher forage production than those with less evenly distributed precipitation down on this end. We also specifically looked at timing of precip. So total precip, yes, is important, but there are some months that are more important than others. And at the statewide scale, our results indicated that, well, actually, so November precipitation had a really strong impact on forage variability. If you just look at the range here of response, there was about, over almost 1,800 kilograms per hectare, which is about equal to pounds per acre. There was a difference in forage production along this gradient from the driest to wettest region. So that was, the biggest sensitivity there. Notably, April precipitation showed the strongest per unit precip influence on forage production. So we're really looking at the slope here. It was, for every 1 millimeter increase in April precip, we saw an increase of about 29 kilograms per hectare in annual forage production. That's a pretty significant response on a per millimeter basis. Then we also looked at comparing drought years versus wet years and the forage production for these two types of years. And these were, extreme wet years versus clearly, statewide drought years. And, production during drought years, not surprisingly, is lower. But also it had much greater spatial variability than in wetter years. Drought in general reduced forage production across the state by about a third. But we saw really strong differences in regional variation. So there were larger departures that occurred in less productive areas. So for example, like along the Central Coast, we saw decreases, of over 40% on the west side of the Central Coast in drought years. We also, in terms of drought versus wet years, thinking about what are the climate and environmental variables that are driving that variability, and do they differ? Do we see different relationships between drought and wet years? And we saw, that there was a difference in the dominant factors controlling driving that spatial variation of forest productivity. So compared to drought years, compared to drought years, the relative importance of precipitation amount decreased during wet conditions, while the distribution of precipitation became equally important with precipitation amount. So we still see precip amount and distribution are the most important variables in drought and wet years, but you can see their relative importance is more equal in wet years. And so just kind of like so just a few of the major points that we found in looking at predicting forage productivity on California rangelands was that, well, forage production, showed really large spatial variability across this entire area. And precipitation amount, especially precipitation amount in the months of November and April, was the dominant driver of forage production variability. And this was particularly true in drier ecoregions and during drier years, a little less true in the wetter regions. And in addition to amount, precipitation distribution was also important. And we did see some different relationships between environmental drivers and forage production under drought versus wet conditions. So looking at the impacts in drought versus wet years, there was some differences in how the drivers were behaved. So that was looking at predicting what is the spatial and temporal variability of rangeland productivity, and really kind of understanding what are the climate environmental factors driving that spatial variability. The sort of next natural step was, well, what are the impacts of climate change on rangeland productivity? It's a big question. And we specifically looked at, so how do changes in weather and climate regulate annual rangeland productivity across ecoregions? And then how will rangeland productivity respond to climate change across ecoregions? And again, we used similar methods in using satellite data, as well as combining this with climate projections under different greenhouse gas emission scenarios to kind of look at the response at different time points. And I'm just going to show a couple of the predictions that we came up with. So for the first question, how do changes in weather and climate regulate annual productivity across these ecoregions? We started with these broader ecoregions, and actually we ended up subdividing them into 23 different sub-ecoregions, and we built specific models for each of those sub-ecoregions. Because as I showed earlier, a lot of these local level impacts, there's a lot of variation in how individual sites will respond. So we further subdivided these into these different sub-ecoregions. And we looked at, what is the sensitivity of the interannual rangeland productivity to these factors? And just like we found in the coarser ecoregion models, across all the sub-ecoregions, precipitation amount and precipitation distribution were the most important variables in the model and in most of the sub-region models. And we found that productivity was most sensitive to growing season precipitation amount, with productivity, of course, increasing with greater growing season precip. And also, again, indicating the importance of seasonal variability of precip. And we found that years with more evenly distributed precipitation throughout all of the months of the growing season had higher productivity. So in looking at so the next question, how will productivity respond to climate change across these different ecoregions? We found that, well, not surprisingly, rangeland productivity was highly variable at the local level. And so these are some maps that we developed based on the climate change projections under different greenhouse gas emissions. This is for what we consider the intermediate scenario. And this is looking at what are the changes basically in productivity relative to the current long-term mean by mid-century and by end of century. So red being decreases in productivity and green indicating increases in productivity relative to current conditions. And interesting, what we found was that in these projections, the future reductions in forage productivity were predicted to occur mostly in moderate to wetter areas. So such as the north coast up here, the NCCR, the central and southern Sierra Nevada, and relatively kind of wetter portions of the central coast. And so this was a little surprising. We found that less evenly distributed precipitation during the rangeland growing season contributed mostly to this outcome. So projections of less evenly distributed precipitation, and these kind of wetter areas were further impacted by projections of warming mean air temperatures. In contrast, we saw future productivity increases were mostly found in drier and less productive sub-ecoregions. There were, of course, a few exceptions. Some of the driest sub-ecoregions of the Central Coast showed potential benefits, say here in green, from a predicted increase in precipitation, with additional benefits from predicted increases in minimum temperature. And so basically, warming the warming winter minimum air temperature potentially is enhancing or predicted to enhance productivity, in a lot of these subsections. However, you can see we still have some of these areas in bright red here. There are predicted increases in maximum temperatures, and that causes significant productivity declines in some of these drier subregions, but basically in the CCR as well as this North Coast Interior Range. Just as a caveat, though, I don't want to get the Central Coast folks down here too excited about potential increases in productivity, because there is quite a bit of uncertainty in all of these global change models about how precipitation will actually change and under these projections. Not all of these models agree that precipitation, about what the total change in precipitation will be. Some of these models agree we'll have a drier future, some say we'll have a wetter future, and this is sort of a composite of all those predictions. They do, however, all agree that precipitation will get much more variable. So, looking at this, all of this in total, these approaches potentially have the potential to forecast forage production in both kind of the near real time, so on a seasonal basis, to provide land managers with information to make proactive grazing decisions. And potentially down the road, the thinking is that they can help with forecasting actual forage conditions relative to changing climate. And particularly we're thinking about products and like the U.S. Drought Monitor, for example. These types of maps can provide finer spatial resolution, so sub-county level resolution that's directly related to forage productivity that can help inform some of those types of efforts. So where are we next in this rangeland remote sensing effort? While we're developing, increasing our capacity for seasonal forecasting, we have over the last couple of years expanded on the ground monitoring. As I mentioned earlier, we have about 17 county-based cooperative extension farm advisors that represent about 33 counties across the state, and working with local ranchers and land managers to collect that really vital on-the-ground data for the validation and calibration of these models. And so in the next year or so, we're going to be developing these decision support tools, and specifically reaching out and working with stakeholders, the end users of these products, to integrate the on-ranch field data, and with the goal of getting that locally calibrated, co-designed and hopefully then trusted decision support system for these really uniquely variable California rangeland annual systems, and really looking to help folks proactively manage for drought risks and increasing frequency of drought risks into the future. So if you're interested in knowing more or want to get involved in some of these some of this co-development process that we're going to be starting, you can contact me here or watch these spaces. I'm just going to pop up here real quickly some of the supporting literature on this. This was a bit of a whirlwind tour of the immense amount of effort that went in to developing these models and these predictions. And like I said, all led by Dr. Grace Liu, who got her PhD with Yufang Jing, my collaborator on all of this work. Okay. My thing is my mouse is stuck. Let's see. There we go.
Great.
My mouse is sticky.
Well, thank you, Leslie, very much. And one of the questions that came up in the registration process was, in years like we experienced last year, where there seemed to be multiple drivers in terms of forage production, whether it was early emergence from dormancy and some of the woody vegetation or depletion of soil moisture. How do those changes all play into the predictive model in terms of forage production? Are there things that you'll be looking at in addition to the parameters that you looked at in these initial studies?
Yeah, as we continue, there's it seems like every day there's new advances in collecting more and more of this both climate, environmental, biotic, and abiotic data that can be fed into these models, as I understand. And I think that, I didn't go into it, but we also did look in depth at some of the topographic and soil information of a lot of these sites. What really popped out in terms of importance, of course, was that precipitation total and timing. But there's also a lot of nuances and detail in the rest of those variables as well. And frankly, some things that kind of raise questions about why are we seeing that, that effect from that change in soil moisture, for example. And so I think, there is a little bit of, I don't want to get outside my wheelhouse of this model building and projection, but as I understand it, as we continue to develop these tools and we can continue to fine tune them as we get more and more reliable data into these, and particularly for the GCMs, the global change models. I think as we learn more and more, we can get more fine-tuned predictions. Because it's interesting, whenever we talk about climate change on rangelands and the impacts, we always think that and we actually said this in an earlier paper. We always think that it's going to be a drier future, more drought, more severe drought. And so those drier regions are going to get hit harder. But then when we did the actual projection, it looks like those drier regions actually, they are not going to get hit as hard. They're not going to be, productive gardens of Eden, but they're not going to, potentially, maybe they're not going to get hit as hard. And that's because some of those really interesting interactions between some of these variables. A lot of it is also the uncertainty of precipitation, projections. But then also that interaction of, the temperature, minimum air temperatures in January, for example, versus, those maximum air temperatures the rest of the time of the year with that variability in precipitation. All of these things interacting, which we, until recently, didn't have the statistical power or capability to really disentangle all of that. A lot of the work that has been done that, we were able to do was kind of looking at each of these changes one by one. And so, with these, machine learning type models, they can really crunch through a lot of this, this whole big data approach and bring together a lot of those, simultaneous but contrasting effects interactions.
And I would just remind everybody who's on tonight, if you do have questions, to put them in the Q&A pod. A question that occurs to me as a sheep guy is the relationship between quantity and quality,
Mhm.
and the speed at which we go through that spectrum of forage quality. Do we know enough about kind of the relationship between forage quality and phenology to start being able to think about, you know, in those short years, how long do we have to get the
Mhm.
nutrition out of the forage, and how does that interact with some of these quantitative models that you're working on?
Yeah, I think I think there's some folks in other parts of the Western U.S. that have been thinking about that as well. As you know, the annual grassland quality goes quick,
Yes.
but I think that is an excellent additional layer we could add on. So once we get these tools sort of operating, how can we layer in some of those really important questions? And that's some of the things I'm sure will come up, but we want to make sure that we don't miss later. So that's why we want to make sure that when we, we truly want to do this co-development process of this tool and ask folks, what are the things that you're interested on the back end of coming out of this?
Mm-hmm.
And, I'm sure forage quality is gonna pop up as a, primary interest. And so how can we do that? How do we do that in the next iteration?
Right.
We want to make sure we build something that people will actually use and it's trusted to use in making these decisions.
Leslie, we had a question come in that kind of jumps off of what you were just saying. So could you talk a little bit more about how you envision land managers using the data to inform grazing and land management planning decisions?
Yeah, so one of our first tasks is to kind of come up with these near real time sort of seasonal forage predictions. And this is kind of in parallel to what's been going on in the Midwest, or sorry, in the Great Plains with grasscast, for example. And so creating these tools so folks can get a little bit better idea of, okay, given all the information we have to date, what might this coming season or the next few weeks, what might it look like based on the information that we have? And I think, it can help folks get a more wider, expansive view of the land that they're managing. These are, expensive acreages, as you know, and help them potentially make those really critical decisions, as early as possible. We always talk to folks, and hear about how trigger dates are so important, and thinking about when I need to make these decisions. If they can get information that helps them make that decision with a little more confidence a little bit earlier, then I think that could be really critical.
Along those lines, Leslie, do you see some of these tools being helpful in other areas beyond kind of forage production and consumption, and thinking about planning for fire season, for example, or beginning to get a handle on predicting fuel loads in some of these systems?
Yeah, I mean, absolutely. I think some of the opportunities are endless here. There's already some folks that have been working on some different models. There's folks all around the country that have been working on similar types of efforts for quite a while now, and have been looking at forecasting fuels, for example. And I think that is something that also could be easily integrated into this. Mm-hmm. I think also as the technology continues to advance, we can also potentially look at, and this is a big challenge, annual grassland, but look at invasive species, and and potentially the spread and introduction of new invasive species. It's a little bit more challenge for us because we already have annual grasses, and our invasives coming in are annual, so getting those signals is going to be difficult. But potentially down the road, and with advances, we could maybe get to that point. And so, and as some of these invasive species can also contribute to fire cycle as well.
Absolutely. Grace, any more? Go ahead.
Oh, I have a question that might be a little Northeastern California specific, but so I'm wondering, I know that one of the challenges we have in this region with remote sensing, we don't quite fit what folks are doing with like GrassCast or the Rangeland analysis platform in the plains, but we don't quite fit the annual system either. And we a lot of canopy cover to contend with regardless of what direction you go in. So do you have any thoughts about, how advancements down the road may be able to help like the Intermountain region get involved in more of this?
Yeah, and an added wrinkle to that is snowpack and snowmelt. It's also an important contributor to that system as well. And that is something that I think once we can get a handle on the annual grassland system, we are thinking about how can we expand this to these other systems as well. And I think, some of the work that's already been done, like in the Great Basin, for example, has relevance as well. I'm not sure that I'm not sure that they've been incorporating snowpack, snowmelt into their models or not. They may, but that's something also to think about, reaching out to those folks and, seeing what is the, what are some of the synergies there? The other platforms you mentioned, it's also worth just taking a look and seeing how they're predicting versus what you're seeing on the ground. And there's been a lot of these different groups are, doing these validation efforts where they're sending out folks and, out into these landscapes that they're making these predictions on to actually see, okay, what is the actual correlation there? And that's kind of what I described, kind of where we're starting, just because the annual grassland is such a different beast.
Yeah, that makes a lot of sense. Thank you. Well, I think that does it for questions this evening. So thank you so much, Leslie, for sharing your expertise, really interesting work, and looking forward to hearing more updates on these projects in the future. So that concludes our final session of the 2022 Working Rangelands Wednesdays Drought Series. Thank you so much to all the folks who logged on tonight and to all of those who attended throughout the series. And we'll keep you all posted on when we decide to pick up Series 3. So thank you for joining us and have a good evening.